All right, so yesterday we left off, listen up, section 1-2 with bound, or bounded up, or I'm sorry, bounded above, bounded below, bounded here, bounded there. How did you do on your homework with the bounding questions? There was one question that you might want to bring up. Anybody come across a question that you didn't understand why it was bounded both above and below? Very good. Thank you. There's the question. So what if you had a, I must have put all my pens back. What if you had this? Let's bring this up. So let's add this to our bounded section. Now, by process of elimination, you could figure out the answer to this, but you need to know why. So let's say that you had the following graph. The answer is bounded above and bounded below. Why? Why is it both bounded above and bounded below instead of not bounded? Take your horizontal line and work your way up. Is there a minimum to this graph? It's whatever this number is. Let's say it's 3 here. It's got a minimum of 3. Is there a maximum? 3. It's its own minimum and its own maximum. So it's kind of a weird graph where the minimum, the overall minimum, the overall maximum is the same thing. So it's bounded both above and below. It has a maximum and a minimum. So that's a weird thing. Okay, let's talk about we got through and we did not get to the even and odd. Is that correct?
Yes.
Okay. So even versus odd functions. We can determine whether a function is even or odd based upon looking at the graph, looking at a table of values, or algebraically. So I'm going to show you all three. So let's look at the first function. Let's let it be f of x is equal to x squared. We'll make it simple. It is an even function if and only if I replace every x in the function with a negative x, and I get the same function. I replace every x in the function with a negative x, and I get the same exact function. In other words, there are no sign changes, nothing changes in the function. So it would look like this. F of negative x is equal to, and wherever I have an x in the function, this happens to be a simple one, I'm going to replace every x with negative x, and I'm going to evaluate what happens. So in this case, I get f of negative x equals, when I square a negative x, what do I get? X squared. Compare the original f of x to the f of negative x. Are they the same or different? They're exactly the same. So there has been no sign change. Bless you. Now, I could have easily had x squared plus 6 or x squared minus 7. I still would have only had substituted in negative x for the x, and I would have had a plus 6 or a minus 7, whatever that constant number would be. That's not going to change the constant number either. So if an even function has a constant to it, it'll still be an even function. So if a function has a constant to it, it'll still be even, because you can't change the sign of a constant by putting in a negative x. Also a clue, the fact that it's even, we have an even exponent up there. Doesn't mean it's definitely even, but it's a possibility that it could be even. The other thing that we're going to look at would be the graph and the table of values. So if I created a table of values for this particular function, look at what happens. So I'm going to start with negative, because it's my lower number. If I take negative 3 and square it, I get positive 9. Negative 2 squared is 4. Negative 1 squared is 1. 0 squared is 0. 1 squared is 1. 2 squared is, whoops, 4, and 3 squared is 9. I'm going to plot the points that I can plot on the graph, but please note that when x was negative versus when x was positive, was there any sign change? No sign change. Now that doesn't mean that y is positive. I could have had, I don't know, a -2 in front of the x squared. So whatever happened to x squared would be multiplied by a -2 when all of these values have been negative. So these values could all be negative as well. They just have to all be the same sign. So plot those points. So I can plot, you okay? I can plot -2, +4. I can plot -1, +1, 0, 0, 1, 1, and 2, 4. So when you look at the graph of an even function, even functions are symmetrical with respect to the y-axis. In other words, I could make a fold on the y-axis, and the graph will fold onto itself. Is the y-axis the axis of symmetry for that parabola? Yes. So this parabola is symmetrical to the y-axis. So all of those three things tell me it's an even function. All three things. Replacing the function with a -x has no change to the function at all. Symmetric with respect to the y-axis. Whether I put in a positive or a -x creates no sign change for the y. I'll tell you it's even. Well, let's look at something that's not even and it's not odd. So how about, we looked at this yesterday, I believe. X equals y squared. So we're going to switch the squaring on the x and the y. So let's look at the table of values associated with this function. Well, it's really not a function, with this equation. I'm going to choose values for y because it would be easier than choosing values for x. So if I choose -3 for y and I square it, I get a 9 for x. If I choose -2 for y and I square it, I get a 4 for x, and so forth. So -1 gives me a 1, 0, a 0, +1, a 1, +2, a 4, and +3, a 9. So notice this time you have sign changes with the y. No sign changes with the x. So let's plot the points that we can plot. So I can plot 4, -2. I can plot 1, -1, 0, 0, 1, 1, and 4, 2. Tell me why this is not an even or an odd function. It's not a function. How can it be even or odd if it's not even a function? Now notice that this particular one does have symmetry with respect to the x-axis. Not all neithers, because this would be considered neither, not all neithers are symmetric with respect to the x-axis. This one just happens to be. But if a graph is symmetric with the x-axis, it is neither even nor odd. So let's look at an odd function. Can I flip this? I'm thirsty, I have no straw. All right, here we go. So an odd function. Let's look at f of x equals x cubed. What's the first thing you notice? Odd function. Looking at that function, what do you notice? Isn't that an odd exponent? It could be a clue, could be, not necessarily. It could be a clue that it's an odd function. You might be thinking that. Notice this time, when I put in -x for every x in the function, I should come out with the opposite of the function. And what that means is every single sign in the function should change. Not some of them, but every term's sign should change. The only time that isn't necessarily, the only time it doesn't necessarily look that way is if you have a fraction. So we'll do a fraction once so that you can understand the difference when it's a fraction versus just a polynomial. So let's go ahead and substitute in for our x. So if I have f of negative x, I am replacing every x in the function with a negative x. So what happens when I take negative x and cube it? I get a negative x cubed. So if you compare the original to the new, isn't there a sign change? So with an odd function, all terms, and that's plural possessive, all terms, signs, must change. Now if I tacked on a constant onto this original function, a +6 or a -7, plugging in this negative x has no effect on the sign of that constant. So that constant, if I had a +6 here, it would remain a +6 here, which means that the constant sign would not change. Anytime a polynomial has a constant attached to it, it will never be an odd function, because you can't change the sign of that constant by putting in a negative x. So it will not be odd. So it's not possible. So you might keep that in mind. And you might over here want to write yourself a note that all terms, plural possessive, signs stay the same. So let's look at the table of values for an odd function and look at its graph. So I'm going to create a table of values, x, y. My x is -3. If I cube a -3, I get a -27. If I cube a -2, I get a -8. Cube a -1, I get a -1. Cube a 0, I get 0. Cube 1, I get 1. Cube 2, I get +8. Cube 3, I get +27. So I can graph 0, 0, and 1, +1. And then 2, +8 would be somewhere way up here. So my graph ends up curving up infinitely. Whereas -1, -1, and then -2, -8 would be all the way down here somewhere. It ends up curving down in opposite directions. So one end of your graph is up and one end of your graph is down. That's very typical for an odd function. And you'll see why that is. Because notice here, when I change the sign with x, doesn't the sign of y change also? Right? So unlike with the even function. Then this particular graph, if it's odd, it has symmetry with respect to the origin. How do you tell if something is symmetrical with respect to the origin? Two transformations occur. You're going to take part of the graph and you're going to reflect it over the y-axis and then reflect it over the x-axis. It doesn't matter which one you do first, you'll still end up in the same spot. So if I were to take the first quadrant here and reflect it over the y-axis, I would get, give or take, something that looks like that, correct? And then if I were to take this and reflect it over the x-axis, wouldn't I end up here? That's how you know if something is symmetric with respect to the origin. The two transformations take place. And furthermore, the points that are equal distance from each other on from the origin, like for instance -1, -1, 1, 1, or -2, 8, 2, 8, they're the same numbers, but just their signs have changed. So you can check reflection that way. They have all the same order pairs, but the signs are different. Now, if I had an ordered pair that had a sign of, let's say, -5, +2, what would be the reflection around the origin ordered pair? 5, -2. So both signs change on the x and the y. So they're not necessarily going to be both positive and both negative. Is that graph bounded? No, it doesn't have an overall minimum, and it doesn't have an overall max, right? What about this graph here? Is this graph here bounded? Where? Below. I just thought I'd throw those in. All right, so let's look at some examples here. So let's put, we'll put it in our calculator at the end. Let's look at our algebra for this one first. Determine whether it's even or odd. It's x squared. What do you propose it might be? It might be even. Does a constant affect the sign in an even? Nope. So we've got f of -x is equal to -x squared minus 3. So I'm replacing every x with a -x. So I get f of -x is equal to, I square -x, I still get a +x squared minus 3. So compare the original to the new. Are they the same or different? Exactly the same. No signs have changed. So there was no sign change. So just based upon the algebra, I know that that's an even function. But we're going to support it with a graph. So we're going to throw it in our calculator. So I've got x squared minus 3. So it happens to be a parabola that has its vertex at -3 on the y-axis. And it has zeros about there. Is this graph bounded? Yes. Where is it bounded? Below. What does this graph need to be symmetrical to? The y-axis. Is the axis of symmetry to that parabola the y-axis? Yes. So based upon its symmetry, it is also even. So I could give you one or the other and ask you, is it an even or an odd function? You have to be able to tell me, based upon just the graph and not knowing the equation, or knowing the equation and not having a calculator, and being able to use the algebra. All right, so let's look at B. B's highest degree is what? Squared, so it could be a even function. It's possible. So let's look at the math associated with that. So g of -x is equal to -x squared minus 2 times -x minus 2. So I'm putting in that -x for every single x in the function. So I get g of -x is equal to square -x, you get x squared. So far, so good. -2 times -x is a positive 2x minus 2. Ooh. Do you know what your professor in college is going to do when you do that? They're going to kick you out. You know why? Don't yawn loudly in public. You're hurting my feelings. You see me crying? Just kidding. I'm very tough. All right, so my x squared did not change, science. But didn't my -2x change to a positive 2x? And then the constant stayed the same. You cannot have in an even or an odd function some staying the same and some changing. They all either have to change signs or none change signs. You can't have some and not the other. So in that case, I know that this is a neither. And so when I look at the graph, I should see that the graph is not symmetric to the y-axis and the graph is not symmetric to the origin. So let's go ahead and graph it. I expect the graph to look like a what? A parabola. So I want to find where that minimum value is, the vertex. So I'm going to do second function, calc. I'm going to select minimum. Well, that's a new one. I've done this for days. That's close enough to what number? 1. And I'll bet you, you have to be smarter than your calculator sometimes. If I plugged in 1 into the function, what would I get? 1 squared is 1, minus 2 times 1 is -1, plus a -2, isn't that -3? So sometimes your calculator doesn't quite calculate it accurately because of maybe where I put the points, I don't know. But my point is it's at 1, -3. And the intercepts appear to be at 1 and 3. No. Yes. -1 and 3. Where's the axis of symmetry on this? X equals 1. So that is not the y-axis, so it makes sense that it's neither. Nor is it symmetrical to the origin. There's not even a point at the origin. It doesn't have to have a point at the origin, but I cannot do any reflections on that graph and make it reflect onto itself. It's just not going to happen. All right, so let's look at the last one. The last one is one that you will definitely run across if you haven't done your homework yet, which you shouldn't have for this section, this part of it. The fractions can cause some issues. So let's look at this particular fraction. Before I even start, I know that there's restrictions on my domain. Why? What can't be 0? Yeah, the denominator right here cannot equal 0. So before I even graph, I'm going to get my vertical asymptotes in place. So I'm going to take that whole denominator, 4 minus x squared, and set it not equal to 0. And you could move the x squared to the right by adding it and then taking the square root of both sides. You'd have to remember to do plus minus, which 80% of you forget. Or you can factor it as a difference of 2 squares. So I've got 2 plus x and 2 minus x. So x cannot equal -2, and x cannot equal 2. Those are your 2 vertical asymptotes. So I'm going to put those in because they were going to help me with the shape of my graph. Because this is kind of a funky graph. Anytime you have a fraction, it's always interesting. And what you will discover is this is going to have no horizontal asymptote, because we're going to talk about those shortly, but it actually ends up having a slant asymptote. So at this point, I'm going to go ahead and graph it. Make sure you use parentheses with your denominator. So when I graph it, isn't that fun? Do you see your vertical asymptotes in there? Yep. You see these weird swoopy things. So I'm going to find out exactly where that point is crossing the x-axis. I have a guess as to where it's crossing. What's your guess? 0, 0. But let's double check. So second calc, 0. I want to move to the left. And to the right. Calculator's thinking really long and hard on that one. And you get an interesting answer. Happens often. Plug 0 into the original function. What do you get? 0. So here's another instance of where you need to be smarter than the calculator. Whenever it has like a negative or a positive something point times 10 to the negative 33, isn't that a lot of decimal places? Isn't that number super duper close to 0? So those of you who think you'll never ever have to use math in life, I asked my brother, who's an engineer, Ray, do you ever use calculus? He goes, I use it every day. Well, he's an engineer. But I go, no, really, do you understand calculus? Because it's probably been 30 years since he's had calculus. He goes, oh, I could teach a calculus class. And he could. because he has to know his math that well to determine when he puts something in his calculator, you know, is it coming out correctly or not? Because your calculator is machine. So please do know your calculator well. So that is 0, 0. And then it is hugging this asymptote, which is why we put it in there. It's going to help us with our curve of that asymptote. Then we have a swoop. Only because I know I have a slant, I'm going to use that to help me with my swoop. So you can kind of see the slant going through here on your graph. We'll learn how to do those later. But there's an asymptote that's actually at a slant going through there. All right. Is this graph bounded, by the way? Yes or no? No. Could I restrict the interval and it still be bounded? What if I restricted the interval to negative infinity to this fence, which is negative 2? So if I restrict it, is it bounded? Yes. How? Below, because it's got a minimum, right? If I restrict it from positive 2 to infinity, is it bounded? Yes. How? Above. If I restrict it from negative 2 to positive 2, is it bounded? No. There is no max or minimum in the middle. Right? Okay, so let's now talk about the graph. Is it symmetrical to the y-axis? Definitely not, right? Okay, is it symmetrical to the origin? I have this S-curve going in opposite directions. That's a real big clue that it is highly possible. Plus, if you've got part of the graph in diagonal quadrants, like our swoops are in quadrant 2 and 4, that's another clue that it could be symmetrical to the origin. So I'm going to go ahead and try to reflect for you. So this part right here, I'm going to reflect over the y-axis, which means it goes this way, give or take. Would you agree? And then if you take that and flip it back over the x-axis, won't it become that part of the graph? So that part is symmetrical to the origin. And then this swoop here, I'm going to reflect over the x-axis. So it looks something like that, give or take. And then can't I reflect it over this way? So the swoop is also symmetric to the origin. So what kind of a function is this? Just by the graph. This is odd. So then you're going to support it with proof with algebra. It's going to be a little bit harder. So h of negative x is equal to negative x cubed divided by 4 minus negative x squared. Make sure you're using substitution parentheses. So I'm putting a negative x in each of those parentheses. I end up with, in the numerator, a negative x cubed. And in the denominator, this negative x squared becomes a positive x squared, but there's a minus in front of it. So it appears as if the numerator has changed signs, but the denominator has stayed the same. How can it be odd? You have to go back and think about negatives with fractions. If I have the fraction negative 2/3 with a negative hanging out to the side, would you agree that I can put the negative either in the numerator or in the denominator, but not both places? So a negative with a fraction, for an odd function, the negative can only be in one place, either the numerator or the denominator. So I'm going to take this negative out of the numerator. Seems the easiest to factor it out from. And wouldn't you agree that h of negative x is equal to negative, I'm taking it out of the numerator, I get x cubed over 4 minus x squared. I purposely am using parentheses. Because go back and look up at the original notation here. It says f of negative x is equal to the opposite of the function. Isn't this h of negative x is equal to the opposite of the function? So all I did was take that negative from the numerator and I pulled it out to the side. So when you have a fraction, you are not going to see all the sign changes on all the terms because it's not the way fractions work. If I had this as a negative and both of those I could factor out a negative, I'd have a negative over a negative, which is a positive. So my point is also, if you have a fraction that's an even function, you will see all the signs change. It's kind of weird on a fraction because I could factor a negative out of the top, a negative out of the bottom, and the negatives cancel, and I'm left with my original function that actually didn't change. So be careful with the fraction ones. That's one where they're going to get you with it. I probably will not give you a fraction one on your test. Maybe for graphic purposes I would, but not for the algebraic. And that might be an extra credit one to see if you remember that. All right, so questions on that, are we good? What's up?
Why for the vertical asymptote part do you go from the equal sign so not equal to 0, and then x equals 0?
If you went ahead and left that in there, because technically the equation of that line is not a not equals, it's really referred to the function. But if you went ahead and left x does not equal, and by the way, we need to label these, x equals -2, x equals 2. Typically, we won't label a vertical line as a not equals. That's the only reason why. But if you put it as a not equals in there, I'm not going to ding you for that. But that's a good question. And what was the other part? Was that the whole thing? Okay. All right, any other questions before we move on to asymptotes? Okay, so let's talk about asymptotes. You should have had these in 3-4. Hopefully you remember them. But we talked about vertical asymptotes. In other words, your domain is restricted if there's a variable in the denominator or a variable underneath the radical. For horizontal asymptotes, make sure you learn how to spell the word asymptotes. It's got a P and 2 T's in there. We look at the degree of the numerator and compare it to the degree of the denominator. So there's only 3 possibilities. The degree of the numerator can be less than the degree of the denominator. That's one possibility. So you might want to put here that I'm referring to the degree of the numerator. So as I look at this fraction here, this monomial, what's the degree of the monomial? What's its exponent? 1. So the degree of this x is 1. How do you find the degree of a whole polynomial? Yeah, you find the degree of each of the terms separately, and whichever degree has the largest degree, the whole polynomial carries that degree. So that's a degree of 0, a degree of 1, a degree of 2. So the whole polynomial has a degree of 2. Don't add them together. It's whichever term has the biggest degree. So in our case here, for our horizontal asymptotes, the degree of my numerator compared to the degree of my denominator, I have a degree of 1 in the numerator and 2 in the denominator. So isn't 1 less than 2? So I have this situation here. 100% of the time, the horizontal lines go through the y-axis, so it's always y equals. And when the degree of the numerator is less than the degree of the denominator, 100% of the time it's y equals 0. So I know that on my line here, I'm going to have a horizontal asymptote. In other words, my graph is not going to cross it at y equals 0, which is the x-axis. I'm going to draw a dashed line horizontally. And you must label it y equals 0, especially when your asymptote is one of the axes, because it's really hard to see that dashed line. And if you label it as y equals 0, I understand that you're telling me it's an asymptote. All right, so there's 2 other situations that might occur. The degree of the numerator could be exactly equal to the degree of the denominator. And in that case, it's still y equals, but you are going to take the ratio of the leading coefficients. What I mean by the ratio of the leading coefficients would be the highest degree term. It's not the first term in the polynomial, it's the term that we determine the degree from. You will take the ratio of those coefficients. And so I'll show you some examples here in a minute of what that looks like. And you've got several problems in your homework that do that. And the final situation would be if the degree of the numerator is greater than the degree of the denominator, you will have no horizontal asymptote. But it is possible you could have a slant asymptote, which you don't know how to find yet. And we had an example of that right, I'm trying to get it so you can see it, right here. The degree of the numerator on 9C was 3. The degree of the denominator was 2. 3 is greater than 2. We have no horizontal asymptote, but we do have this slant asymptote going on, which is easy to see because you can see it with those swoops. Here we go. Let's finish graphing this one. So we have to identify any horizontal or vertical asymptote. So we did the horizontal. Let's look at our vertical. What restricts our domain? That's our vertical asymptote. So how do we restrict it? What's the issue here? We have a denominator, so that denominator cannot equal 0. So x squared minus x minus 2 cannot equal 0. We can factor this. What factors of 2 subtracted would be 1? So 2 and 1. 2 is the bigger one. The middle term has a sign of negative, so the bigger of those two factors gets that negative. What does the 1 have to be? If the 1's negative, we have a positive 2, and they add to give you 3. So it's positive. Set each of those equal to 0, and x will equal 2, and x will equal negative 1 are your vertical asymptotes, and so probably need to put a not equals to in there also. So I'm going to put those in. And don't forget to label those. Because they go through the x-axis, it is x equals negative 1, x equals 2. Now we're ready to use our calculator. Your calculator is not going to show those asymptotes. Or if your calculator does show the asymptotes, it looks weird. All right, so we have x divided by parentheses, x squared minus x minus 2. There we go. Do we see the vertical asymptotes? Yep. And I see my horizontal asymptote right there, going right through there is y equals 0. So let's find the 0 here. And by the way, your graph can cross that horizontal asymptote in between two vertical asymptotes. Weird but true. All right, so let's find the 0. Second calc, 0. I want to be above the axis and below the axis. So I get 0, 0. And I'm hugging that axis and swooping over here and hugging that axis. Then I have a swoop here and a swoop here. Is that graph bounded? Everybody? No, there's no overall minimum or maximum. From 0 to what number would be my first, from negative infinity to what number would be my first restriction? To negative 1. Is that bounded? Everybody? Yes. Is it? Yeah. It has a definite maximum, right? So is it bounded above or below? Above. What about between here? No. What about here? Below, right? Just below. Okay. So we've done our asymptotes. Let me just change one little thing on here. So let's take the same graph, but instead, let's now change this exponent to squared. What's the degree of my numerator? So my numerator versus my denominator. My degree of my numerator is 2, and my denominator is 2. Aren't they equal? So that means that my asymptote is y equals the ratio of the coefficients of the leading terms. So my leading terms are x squared and x squared. What are their coefficients? Coefficients. 1 and 1. So wouldn't my axis of symmetry be y equals 1? Watch what happens if I change my equation and y equals. So I get x squared divided by is it approaching y equals 1? Hard to tell, but it's definitely higher above than the last graph was, right? Well, what if I change the coefficients to, oh, let's do 10 and 5. So my coefficients or my degrees are the same, but my coefficients this time have changed. I have 10 for the numerator and 5 for the denominator, giving me, oh, let's change that not to 5, let's do that to 2, because I want it to be a dramatic change. Change that to 2. So doesn't that give me 5? Let's make those changes into y equals. So 10 x squared is definitely approaching y equals 5. What if I happen to have one of them negative? So let's change this to a negative 6. So I have a negative 6 over a positive 2, giving me a negative 3. Look what happens to the graph. It approaches y equals negative 3 here, and what happened to the parabola part and the swoops? Everything flipped, right? Reflected over the x-axis. All right, so does that make sense? You have several problems where you have to take those leading coefficients. All right, so let's look at the back page. End behavior. This part would be on the non-calculator portion of your test. So when you do these problems, don't use your calculator because you're not going to get use of your calculator on the test. So on Math Excel, please practice it without a calculator. Copy down the following graphs. This graph has an upward swoop and it's going down, and a lower swoop and going back up. It is approaching y equals 0. The second graph has a point at 0, 0, 1, 1, and, no, I'm sorry, I lied. Let's do 1, 1.5. So 1, 1.5. And let's do 2, 5. So it looks like this. And then it also is at negative 1, negative 1.5, and negative 2, negative 5. And then the third graph has a vertex at 0, 0, and it's a parabola opening up. And the fourth graph has a horizontal asymptote at y equals 3. Math Excel is not going to show you the horizontal asymptotes. You have to make the assumption that they're there by looking at the graph. There is an ordered pair at 0, 0. On the right side of the graph increases and approaches that asymptote. On the left side of the graph goes in the opposite direction. It's like a bird in flight. Now our job is to match the graph with the equations to the left. They're not directly across from each other. What do you notice about all the equations? They're all x squared plus 1. So let me explain to you what we're going to do to find end behavior without using your calculator. Tell me what would happen with this denominator, which is x squared plus 1. How does the plus 1 have an effect as x approaches infinity? In other words, as I replace x with a bigger and bigger and bigger number, how does that affect the value of x squared plus 1? So I'm going to put x squared plus 1 in here. Well, I really don't want to look at that. I want to look at the graph. So I'm going to look at my chart of values, and if I start off with 0, I get 1. That makes sense. 1, I get 2. 2, I get 5. Well, what if I jump to 10? Now I get 101. What if I jump to 1,000? What happened to my 1 being added onto that? If I take that out of scientific notation, isn't it a 1 with 6 zeros? Which is 1,000,000. What happened to the plus 1? What if I put in 10 million? No plus 1. Consider this. If you had $10 million squared, and I came up to you with $1 and said, here's $1, are you going to be excited about that? You have 10 million squared dollars. $1 to you is like less than a penny. Whereas if you have $0 and I give you $1, aren't you jumping up for joy? Because now you can go to McDonald's and have a hamburger. So my point is, this plus 1 has no effect on the denominator as x approaches infinity. So what we're going to do is we're going to take the original function, in this case 3x, and we're going to divide it by what matters in the denominator, which is x squared. The plus 1 does not matter. And you're going to reduce that. So this is 3 over x. Look at that function and think to yourself left hand and right hand behavior. The right hand, as I go to the right, I'm approaching infinity for x. So as x approaches infinity. So as I go to the right of a graph, this graph here, if I plug in a bigger and bigger number, what's going to happen? 3 over 1 is 3. 3 over 10 is 3 tenths. 3 over 100 is 3 100ths. 3 over 1,000,000 is 3 1,000,000ths. What is that close to? 0. So as x approaches infinity, f of x, the value of the function, approaches 0. This is your right-hand behavior. But as x approaches negative infinity, in other words, if I put a bigger and bigger negative number here, negative 3 over 1,000,000 is still close to 0, but just on the negative side, isn't it? It also, the value of the function also approaches 0. That's the left-hand behavior. Left meaning negative infinity, right meaning positive infinity. Which of the 4 graphs, as I go to positive infinity, approaches 0, and negative infinity approaches 0? Isn't that the only one? This one, stay if you want to listen to the rest of it, it'll take me 2 minutes. This one approaches positive infinity from the right. That's negative infinity from the left. So it can't be that one. This one's approaching 3 from left and right, and that one's approaching positive infinity, both left and right. You can quietly leave if you just leave quietly. You don't have to stay, it won't be rude. So look at this one. If I take, so this one matches up to here. If I take this one and divide it by x squared, so I have 3x squared divided by x squared, what do you get? Just 3. Isn't that a constant number? No matter what I do with x, this number stays the same. So as x approaches positive infinity, if I use a bigger and bigger number, I can't change that value. F of x is going to equal or approach 3. Even if I use a negative number, as x approaches a big negative number, negative infinity, the value of that function is still 3 because it's a constant. The only one that approaches a constant value of 3 is this one down here. So those match up. And then this one, if I take 3x cubed and divide it by x squared, what do I get? 3x. So if I put in a big number for x, as x approaches a big positive number, won't you get a 3 times that big positive number? So it just becomes bigger and bigger positively. That's your right-hand behavior. Out of the 2 graphs left over, both of them increase infinitely positive infinity, right? On the right. So look at the left. As x approaches negative infinity, this time you're putting a negative number in. So this one should approach positive infinity. When I put a negative number in here and multiply it by 3, what happens? You get a bigger negative number. So this approaches negative infinity. Isn't this the graph that is approaching negative infinity from the left? That's your left-hand behavior. So this one matches up with this one. And that leaves the parabola for the last one. And here's one. If you take 3x to the 4th, divide it by x squared, they think they understand it. It gives you 3x squared. What was that? Okay, well, hold on. So as x approaches positive infinity, so I'm going to put a big, big number in here. Think a billion. If I square a billion, I have an even bigger number. Multiplied by 3, I have an even bigger. Aren't they both positive? They're all positives. So no matter what number I put in there, the bigger the number gets, won't the value of that function, which is f of x, is y, won't that approach positive infinity? Just a bigger number. If I put a negative number in for x, so as x approaches negative infinity, what happens when I square a negative number? I get a positive number. So, and I multiply a positive number by 3, I get a really big positive number. So on this one, the right and the left-hand behavior are going in the same direction, which is your problem. So it's thinking about in terms of that big number, whether it's positive or negative, and it's getting bigger. Sometimes it'll approach 0 like it did when you have a variable in the denominator of the reduced part. Anytime you have a variable in the denominator, that fraction approaches 0. Every time. Because the bigger that denominator gets, the smaller that fraction is. 1/2 is bigger than 1/4. 1/4 is bigger than 1/8. 1/8 is bigger than 1/10. So that fraction keeps getting smaller and smaller and smaller as the denominator gets bigger. So practice it. Come with questions on Monday.